Waltham College, Oxford, and earned his PhD at Cavendish Laboratory in collaboration with Hitachi Cambridge Laboratory. At present, he is in the group of Professor Maurice Skolnick at University of Sheffield, and he has been in 2003. His research interests mostly concern coherent optical control of excitonic and spin states in semiconductor quantum dots.
So I'd just like to make a few acknowledgements. So essentially I'm going to summarize about the last 4 years of my life in this talk, but I've been helped out by all of these people here. I'd like to give a special emphasis to 2 PhD students who've been working with me, Stephen Boyle and Roman Kolodka at the University of Sheffield, and also just to highlight the UK IERI, who are kind of a UK equivalent of the US Indo scheme that are organising this conference. So I'm quite fortunate in that Ruth has already given a very excellent presentation introducing semiconductor quantum dots. And this talk is going to be much more focused on the coherent control of the excitonic and spin states of these quantum dots. So what I'm going to be talking about is using picosecond laser pulses to manipulate the excitonic and spin states, which we can think of as qubits. So on the one hand, you could think of this as being kind of doing atomic physics in a semiconductor system, or you could look at it as a way of we're developing the tools in order to do quantum logic operations. Now, the talk is going to be organised more along the line of a series of short stories, and I'm going to start by giving a bit of an introduction to semiconductor quantum dots. Then I'm going to present a scheme that we've demonstrated showing some evidence for a kind of 2 excitonic qubit conditional logic operation. Then I'll present a scheme which shows how to prepare, control, and detect a single Hall spin. And then later I will discuss some evidence for excitonic dress states in a single quantum dot. And then later on I will discuss an effect called intensity damping, which is basically a decoherence process which limits the fidelity of the gates. Okay, so quantum dots are artificial atoms. So our dots are grown by molecular beam epitaxy. So what we basically have is a gallium arsenide, and we're growing the crystal atomic layer by atomic layer. And so what happens is you have your gallium arsenide, and then you start to deposit indium gallium arsenide on here. Now, because there is a lattice mismatch between gallium arsenide and indium gallium arsenide, you can only grow a certain thickness of indium gallium arsenide before the strain buildup is so large that the material relaxes to release this strain and forms these small nanoscale islands, which are quantum dots. And then you basically put a gallium arsenide layer on top to just seal off the dots. Now, they kind of look a bit like this. So this is a cross-sectional STM image of a stack of quantum dots. And you basically have this kind of, these lumps of indium gallium arsenide embedded in gallium arsenide. And these sit on a so-called wetting layer, which is effectively a kind of a thin quantum well of indium gallium arsenide. And the point here is that indium arsenide has a different band gap to gallium arsenide. So this forms a nanoscale potential well in which you can trap electron states. And so the basic idea is we have a valence band and a conduction band, and if we excite with a photon of the correct energy, then we'll create an electron Hall pair in the dot. And these, because of the nanoscale confinement, we have quantized energy levels. So these occur at discrete energy levels. Now, the other point to make here is that the confinement gives the quantum dot levels a different energy level compared with the bulk semiconducting material. So you have an energetic isolation of these states from the rest of the material. And so what we have is a system with discrete energy levels, which is energetically isolated, and that is exactly like an atom. So because this is like an atom, it will have a coherent light-matter interaction, which means that we can, if we excite these states with laser pulses which have a time duration which is short compared with the coherence time of these states, their dynamics will behave in very similar ways to atoms. So we've developed a kind of a photocurrent measurement technique for studying a single quantum dot. Now, in the previous talk, the work on nuclear spins was on ensembles of dots. And if you work with ensembles, you've got many dots that can contribute to the signal, and this makes it much easier to measure. Now, if you're looking at a single dot, you have to have a very aggressive measurement technique to be able to detect the state. So we use this photocurrent technique. The basic idea is that we grow a low density of quantum dots, which are embedded in the intrinsic region of an Ni Schottky diode, which is basically a photodiode structure. Now, the idea is I'll have a sequence of laser pulses, and I will excite close to resonance with the excitonic transitions, and I will create electron hole pairs in the dot. Now, because I apply an electric field, the electron hole will tunnel from the dot, and I can detect that as a change in the photocurrent. And so then, for example, if I take a laser and I change the laser frequency, actually there's a better thing on here. So here, this is a kind of a typical photocurrent spectra for exciting with a single laser pulse. Now, the photocurrent is proportional to the final number of excitons created in the dot. And we're taking a laser pulse, which has a Gaussian pulse spectrum, and we're just tuning the center frequency through that resonance. And then we get a rise in the photocurrent, and we get a spectrum which basically is it's a bit like an absorption spectrum, and you can understand the shape in terms of this is just the pulse spectrum of the laser pulse. And that's because we're using a laser pulse whose spectral width is quite large compared with the line width of the quantum dot. So here the pulse is about 20 picoseconds in time duration, which corresponds to about 0.2 millielectron volts spectral bandwidth. Now, the first thing that I can do is I can see if I can observe a Rabi oscillation. Now, a Rabi oscillation is a coherent rotation between the lower and upper states of a two-level system and forms the basis of a single qubit gate. So here's an example of a Rabi oscillation that we've measured. So what we do in this measurement is we take our laser and we tune it on resonance with the neutral exciton transition. Now, the neutral exciton transition basically consists of a crystal ground state in which we have no carriers in the quantum dot, and an exciton state where we have one electron hole pair in the dot. And we can consider this as a qubit because we can label these states 0 and 1. So we start off in the ground state. We tune the laser on resonance. And then what we're doing is we're just measuring the photocurrent, which is a measure of the final exciton population, as a function of the incident power of the laser pulse. So what we're doing here is we're not changing the time duration of the laser pulse, we're changing the Rabi frequency of pulse. So as we change this, we see this oscillation. And you can, if you think of this in terms of a block sphere representation of a single qubit system, where you have 0 and 1, we're basically doing a rotation about this axis. So I think that's a sigma x type rotation. Now, one way of understanding this is to say, okay, if I have a laser, if I have a two-level system, I have a lower state and an upper state, and I excite with a laser on resonance, then I start off in the lower state, and I will get absorption, and this begins to populate the upper state. But then because we're in this coherent regime, it's a reversible process. So we basically get an oscillation between stimulated absorption and stimulated emission. Another way of perhaps looking at this is to look at this in a so-called dress states basis. And here you can think of this, so in the excitonic basis we have two states that are labelled 0 and x, which are split in energy. Now I can shift to a rotating frame and basically think of two states which I'm going to label 0 and x with the excitonic state and with the number of photons in the control mode of the laser, which is n. Now, if in the on-resonance case, these dress states are degenerate, but when I apply the laser, I couple these two states through the optical transition, and I basically split them, forming these kind of a mixture of the two dress states, which is split in energy by the Rabi frequency. Now, I can control. Now, in the case of on-resonance, you have two superposition states, and by controlling this field and the time duration of it, I can control the phase shift that I apply between these two mixed states. And when I turn the laser off, I will have acquired this phase shift, and this gives you a rotation in the final state. And this is in terms of theta, which is the so-called pulse area, and that's proportional to the time integral of the Rabi frequency, which in turn is proportional to the optical dipole strength multiplied by the electric field strength of the driving pulse. Now, of course, in a block sphere, this is a representation of the 0, 1. This is just it's a three-dimensional object. So you don't just want to do a sigma x rotation, you also want to do rotations in the sigma z direction so that you can fully manipulate this block vector. So one way of showing that you can do this is to do a so-called quantum interference measurement, or a sort of a Ramsay fringe type experiment. And here what we do is just to backtrack a little bit. Oh, sorry. Hit the wrong button, I'm afraid. Okay. What I do is I take two pulses, and each pulse has a pulse area of pi over 2. So I'm going to set the power to be here. What the first pulse does is it rotates the block vector through an angle of 90 degrees. And this creates a linear superposition of the 0 and 1 state. Then I wait for a certain time and apply a second laser pulse with a pulse duration with a pulse area of pi over 2. And this creates a similar superposition, but this time with a relative phase difference depending on the timing. And then you will observe an interference. So here we've got the photocurrent, which is the final exciton population, plotted versus the time delay. And we basically see now if you take a close-up here, you see an oscillation, which has the frequency of the time delay, and this decays with an envelope. And this envelope gives you a way of measuring the T2 time. Now what you'll notice here is that the T2 time, the coherence time, is very short for these excitons. And the reason for that is that we're applying this strong electric field, and the electron tunnels from the dot, and that destroys the exciton. So this coherence time is limited by the electron tunneling rate, and that's okay, so it's quite short. Maybe. So I suppose the first thing to say is that quantum dots have a coherent-like matter interaction, and they behave in many ways very similarly to an atom. We've been able to observe Rabi rotations and also quantum interference, which shows that we can manipulate a single qubit. The downside is that the excitons are not very good qubits because A, the radiative lifetime limits the coherence time to about a nanosecond, which is quite short. So even though you can do manipulation on, say, a 10 picosecond timescale, that still intrinsically limits how many operations you can do. And also the measurement technique that we're using, this photocurrent technique, we're kind of deliberately dephasing the dots so that we can detect something. Okay, but what we can do is we can extend this system to look at a 2-qubit case. Now, this work in a sense is a repeat of some work done by Lee et al. That was published in 2003, except they were working on a different type of dot, a gallium arsenide interface dot, whereas this work is on an indium gallium arsenide dot, which indium gallium arsenide dots are probably more interesting as a long-term prospect because the quality of the dots is just higher. So we can think of a 2-qubit system where we label the qubit states with the spin of the exciton. So we can have a ground state which we'll label 0, 0, so that's no excitons in the quantum dot. 0, 1 is 1 exciton of spin up, and 1, 0 is 1 exciton spin down. And then we can have a bi-exciton state, so we have 2 excitons of opposite spin, and we can label that 1, 1. And we can individually address each of these transitions through polarization selection rules, and also an energetic shift called the bi-exciton binding energy. And this is an energetic shift because you've got a different Coulomb interaction strength for having 2 excitons or 1 exciton. So then you can think of this, so in order to do, say, a conditional rotation gate, if you could apply a pi pulse to this transition here, then that will give you a C0 gate, because you will only rotate from this state, you will only invert the state if you are here. So if you're in any other state, the laser pulse will not do anything. But if you're in the 0, 1 state, you will rotate into 1, 1. And if you're in the 1, 1 state, you'll rotate into 0, 1. So what we have is a setup where we have 2 laser pulses that we can delay in time, and we can independently tune the wavelengths. Now, if we focus first of all on this blue curve here, what we have is just a single laser pulse on our sample, and we're just measuring a photocurrent spectrum by scanning the laser frequency through the excitonic transition. So what we get is one main peak here, which is at the neutral exciton, the dot we're interested in. And also we get a few smaller peaks due to other dots which are present in our sample. Now if we take the first pulse and we tune it on resonance with the neutral exciton transition, and we set the pulse area to pi so that we create an exciton, and we set the polarization such that we create an exciton of a certain spin, we then take a second laser pulse which is delayed in time so that there's no temporal overlap between the 2 pulses, and then we scan the frequency of that second laser. Now, if we have, let's see, so if we have the cross-polarized pulses, then what happens is we basically just scan through the laser, nothing much changes, and basically we just get a flat signal. And the reason for this is that we have created an exciton of 1 spin, and we're addressing it with polarization which does not couple to that spin, so there's no absorption. Now if we take a look at the cross-polarized case, we get this additional peak here, and this corresponds to the exciton to bi-exciton transition. And and we can tune this through here. So the main point here is that we can detect an exciton, the bi-exciton state. Now, if I take my laser and I tune it to here, I can then measure a okay. So I take my second laser pulse, I tune it to the exciton to bi-exciton transition, and then basically I measure the photocurrent as a function of the pulse area of this second laser pulse. And when I do that, I will observe a Rabi oscillation between the exciton and the bi-exciton states. Now, because I can see this oscillation, but I only see it if I have all the selection rules set up, what this is basically showing is that we've got the exclusive OR truth table kind of demonstration of the 2-qubit gate. Now, what we haven't done yet is to demonstrate that you can take a superposition state and transform it into an entangled state and vice versa. But we have made this first step of showing that we can get the kind of truth table type operation. Okay, I'll move on to our work on the optical control of spins. Okay, the problem with excitons is that they have very short coherence times, limited by the radiative lifetime. But the advantage of them is that they've got this very strong optical interaction, which means that you can manipulate them very quickly on picosecond timescales. And in a sense, the reason that you have the short coherence times is because you have this strong interaction. Now, on the other hand, spins potentially could be excellent qubits because, as we've seen in the previous talk, they have the potential for coherence times in the sort of millisecond timescales. So, however, in order to control an electron spin using things like electron spin resonance techniques, using radio frequency pulses, the speed of the operation that you can do is limited by the Zeeman splitting that you can achieve. So it's intrinsically going to be relatively slow compared with the optical picosecond control. Now, if you could come up with a system whereby you could have an electron spin as your qubit, which is very robust, and then you can manipulate the electron spin using the charged exciton or trion states, then you could get a kind of best of both worlds situation. So you could get the fast control of excitons plus the long coherence times of an electron spin. So we came up with an idea for not really looking at an electron spin, but looking at a Hall spin. Now, the problem with looking at spins, at least until recently, is that you need, first of all, a method to initialize the spin state. You need a method to be able to detect that spin state so that you can evaluate whether you have or haven't done your operation. So what we have here is a plan for initializing and detecting a single Hall spin, and it goes something like this. This is our device, so it's this photodiode structure. We're going to apply an electric field such that the electric field that we're going to apply is such that the electron tunneling rate is quite fast, but the Hall tunneling rate is quite slow. And you can achieve these very different tunneling rates because the electron and the Hall have very different effective masses. So then the plan is we use a laser pulse which has a pulse area of pi and has circular polarization, and this prepares a neutral exciton state in the quantum dot. Now, if the electron tunneling rate is fast compared with the exciton fine structure splitting, so that's an energy splitting between the exciton spin states due to the electron-Hall exchange interaction, then the electron will tunnel out of the dot and leave the Hall in the spin state determined by this laser pulse here. So the step 2 is we wait for the electron to tunnel out. And then in order to detect this, what we're doing is a kind of a spin to charge conversion using a second laser pulse. So we have a laser pulse which will have a pulse area of theta, and if it's oppositely polarized to the first pulse, then it's possible to create a positive trion in the quantum dot if you've got the energy tuned to the positive trion transition. However, if we have the co-circularly polarized case, then there will be no absorption here due to Pauli exclusion principle, because that would require us to create two Halls of the same spin. Now, if we create these additional carriers, they will eventually tunnel from the dot, and we will detect this as a change in photocurrent. So what this gives us is a way of detecting a single Hall spin electrically. The experiment is very similar to the previous work in that we've got two laser pulses that we can independently tune. So we take the first pulse. So if we have one pulse only, we just measure the single peak due to the neutral exciton transition in our absorption spectrum. We take the first pulse and we tune it on resonance to this peak here. And then we take our second laser and we just tune it through the resonance. Now in the case of co-circular polarization, what we find is we get the high signal due to we've already created one exciton. And then we get this dip here on resonance to the neutral exciton transition. This is because I've got two pi pulses of the same polarization, and they basically combine to act like a 2 pi pulse, which is going to bring the exciton population back down again. However, there's no further features in this spectrum. If I look at the cross-circular case, then I find a flat response at the neutral exciton transition, because to absorb on the neutral exciton transition, I would have to create another, I would have to add another exciton into the dot and that is energetically shifted from this resonance. So it's no longer in resonance, so that will not happen. But I see this additional feature here, and this is due to the positive exciton transition. And as we increase the time delay between the two pulses, we see this feature grow. And we see the feature grow as the electron is tunneling from the dot. Now you do get some additional signal, some peak in the kind of the wrong polarization. And this is because the spin preparation process is not perfect. So there is a possibility of creating the wrong spin state. Now we can use this to make a time resolved measurement of the Hall spin. And we do this by, we have one pulse tuned to here to prepare our exciton. We have the second pulse tuned to the heavy Hall to X plus transition. And then we just measure the photocurrent as a function of time delay between the two pulses. And what this does is it gives us a time resolved measurement of the Hall spin. So here, for example, we have the correct Hall spin state, which just increases due to electron tunneling, and then slowly decreases due to the Hall spin, the Hall tunneling. Whereas with the incorrect spin, we also get a slow rise, but to a much lower level. So what I've shown you so far is that we are able to prepare a single Hall spin, which is a kind of a single shot preparation of the spin, which is triggered to our first laser pulse. I've also shown that we can detect this single spin, and we can, but it's also a detection that we can get time resolved measurements on a picosecond time scale. What we can also do is show a kind of a partial demonstration of a quantum logic gate. It's not a general quantum logic gate, but it's basically a sigma Z gate. And it's going to work something like this, at least in theory. So we have, for the whole positive exciton state, it's basically a four-level system. So we have Hall spin down and Hall spin up here, and then we have a positive exciton with, and these are the electron spins, which we can label them by. And so these are connected by sigma minus polarized light and sigma plus polarized light. Now if I just shift to a dress states basis, so by that, what I mean is I'm just moving to a rotating frame to remove this energy difference between the exciton and the Hall states. And if we imagine that we start off in a superposition here, then what happens is the one state, so I'm going to have my control laser, and it's only going to couple one of these two-level transitions. So this is acting like two independent two-level transitions. I apply my laser pulse. I dress the two states from of one of the transitions. I apply a laser pulse with a pulse area of 2 pi. And what this will do is give us a phase shift of pi on the state that we have addressed. And that gives you a relative phase shift between these two states. And that's equivalent to a sigma Z gate, which is a non-general operation, but it's a kind of first step. So what we do here is, we have two laser pulses. The first one prepares the spin, so that's tuned to here. The second laser pulse is tuned on resonance with the positive trion transition. We then measure a Rabi oscillation on this state. Now, if we have the cross-circular case, we get an oscillation like this. And in the case of 2 pi, that corresponds to our sigma Z gate. In the co-circular case, then basically we don't really get any signal at all. So what we have is conditional Rabi rotation. We're only driving the transition that we address, and that allows us to put a phase shift on it. Now, to further confirm this, what we've done is a series of measurements where we have our two pulses, and the control pulse, what we're doing is we're going to vary the polarization of this pulse. So we're going to mix it between being sigma minus and sigma plus polarization. And what this is basically showing is that the period of the Rabi oscillation changes as you do that. And And what that shows is that only the sigma plus component of this control pulse couples to the transition because you've created a spin. Let me start again. If you create a spin in this direction, it is only going to be the laser. It's only going to be the circular polarized component linking this polarization to a trion, which will couple to this system. So if I vary the polarization of my laser pulse, I will change the period of this Rabi rotation because I'm changing the amount of light in the different polarizations. And so what this is showing is that this system is acting as a four-level system which behaves as two independent two-level systems. So just to summarize, what we have done is we've come up with a scheme to prepare and detect a single Hall spin. I've presented the first observation of a conditional Rabi rotation of a charged exciton. And this is important because it shows that these transitions have atom-like behavior. And if they have atom-like behavior, that says that it's possible to do full optical control of the spin states. We've shown the case that, now in the case of the 2π pulse, this should in principle give you a phase flip, which is basically a sigma z gate on a spin. It's worth pointing out that recently there's been some very good work published in Nature by our competitors showing the full optical control of a single electron spin. And so that's published by, so the main author is David Press. Okay, how are we doing for time? Okay. Okay, so part 4. I'm going to talk about some direct observations of excitonic dress states in a single semiconductor quantum dot, and more specifically the beating between these states. What we have here is a four-level system which basically is the exciton by exciton system. And this consists of our crystal ground state, which is no excitons in quantum dot, and we have two exciton states which are split by a fine structure splitting due to the electron-hole exchange interaction. And these have opposite polarizations. And then we have a bi-exciton state. Now, if I take two laser pulses and I overlap them in time, and I take a very strong laser connecting one of the exciton transitions to one of the bi-exciton transitions, then what I will do is I will couple these states very strongly. And what will happen there is I will split the states with the Rabi frequency of this control pulse. And then if I take a second laser pulse, I can probe this transition here, and I can observe this Rabi splitting between of this state here. And this is a so-called Ortler-Townes doublet. So here's the experimental data showing this. So this is a grayscale plot where black is the high photocurrent and white is low photocurrent. So what we're doing is we're changing the pulse area of the control pulse, and then we're just measuring the photocurrent spectra as a function. So we're just scanning the frequency of the probe laser through the exciton transition. What we observe is a splitting which increases as we increase the pulse area, and that splitting is proportional to the Rabi frequency. And here this is a theoretical simulation of the same, and we get very good agreement between experiment and theory. Now, maybe just to backtrack a little bit. So if we take a look at this four-level system in a so-called dress state spaces, where basically we're going to label the excitonic states and the number of photons in the control mode, then what the predominant effect is that we have two states which are split in energy by the detuning of this laser pulse from the exciton to bi-exciton transition. When I apply this control pulse, that couples these two states, resulting in two mixed states, alpha and beta, which are split by an effective Rabi frequency, which is the square root of the Rabi frequency squared plus the detuning squared. And then when I have the probe from the 0 to n, I will basically observe this doublet, this Ortler-Townes doublet. So the next thing we want to see is if we change the detuning of this control pulse, can we see the anti-crossing behavior between these two dress states, showing that we've been able to form these mixed states. So what we have here, again, it's a grayscale plot. So we're fixing the detuning, the control pulse, and then we're measuring the photocurrent as a function of the frequency of the probe. And when we do that, we observe this splitting, but we see a splitting which changes as we change the control pulse. So you'll see this anti-crossing behavior. Now the green lines are basically showing here where the neutral exciton transition is, and here where you get a two photon absorption which directly creates a biexciton state. So this is where the sum of these two pulses adds up to the biexciton energy. So you'll see that, so you've got the anti-crossing behavior showing that you can create these two mixed states. Now in our system, unlike previous people, we can look at this in the time domain as well as frequency domain. So here we do a set of measurements where we have the two control pulses are, we're basically changing the time delay between them. So here we have zero detuning, and if we measure a series of spectra for different time delays, we get this eye kind of shape. And what's basically happening here is that the time duration of our laser pulse is 20 picoseconds, and it's got a Gaussian pulse shape. And what we're seeing is that the Rabi splitting is following the envelope of the control laser. And if we change the detuning, then we see that, again, we get a different type of splitting, but it's just following the control laser. And what this is showing is that we can control the mixture, the admixture of these dress states on a picosecond timescale. And this is a kind of ingredients for looking at kind of adiabatic control schemes where you, rather than creating a superposition of dress states that you then see beat to give you a Rabi rotation, you're going to manipulate the admixture of the dress states so that you get a coherent evolution from one state to another, but always staying in some sort of eigenstate. So as an additional measurement, what we'd like to do is to observe the dress states, but since we can do this in the time domain, is to look at is to create a superposition of the dress states and to observe the beating between that. Or in other words, to do a time resolved measurement of the Rabi oscillation. So a measurement scheme is like this. So we have a control laser, which is spectrally narrow, and that's very long in time duration. And then we have a probe pulse, which is short in time, but spectrally broad. So you can interpret, and what we're going to do is we're just going to measure the photocurrent as a function of the time delay between these two pulses. So what we're doing here is we're kind of, okay, one way of thinking of this is to say this has a pulse area of pi. And if you consider this to be a delta function, at a certain time I create an exciton. When I create that exciton, I then start to oscillate between these two states in the Rabi oscillation. And by controlling this time delay, I basically control when I kind of gate the control field. So I'm determining for how long the control field is active. Another way to look at this is to say that this control pulse is dressing the two states. So we form a superposition state, and I excite it with a probe pulse which is spectrally broad compared with the splitting between these two states. So I create a superposition of the two dress states, and they beat. And I can control the time for which they beat by controlling the time delay between these two pulses. So here's the experimental data. Now, if you just imagine what's going on in a Rabi oscillation in time for different pulse areas, this is pretty much what you get. So for a pi pulse, we basically just see the laser comes on and we go from the exciton to the biexciton state, and then we get slow decay due to the biexciton relaxation. For 1.5 pi, we go up and then down. 2 pi, we go up and down further. For 2.5 pi, we go up, down, and up again. So you can see that we've basically, on the block vector, we've gone up, all the way down, and we're going back up again. And so on as you increase to 3 pi and 3.5 pi. Now, as you go up to very high pulse area, this kind of interpretation of this data as a time-resolved Rabi oscillation begins to break down because the control pulse is splitting the two levels so far apart that you're no longer efficiently exciting them with the probe laser. What this results in is a slight dip so that the change in photocurrent goes negative. And this is an effect very similar to electromagnetically induced transparency, where you're inhibiting the absorption of the probe pulse by using the control laser. So just to summarize here, what we've done is we've taken an intense laser pulse to couple the exciton and biexciton states. And this forms a Nautler-Towns doublet. We can observe this effect in both time and frequency domain. What we've been able to show is that we can control the Rabi splitting on a picosecond time scale, which means we can control the composition of the dress states on that kind of time scale. And this shows that the various schemes for adiabatic control of exciton and spin states are feasible. We've also done time-resolved measurements of Rabi oscillations in quantum dots. And this is quite important from sort of an aesthetic point of view, because previously people have measured them in terms of the incident power. So as you do this measurement, the power on your sample is increasing, whereas what you would really like to do is to observe this in time. So I move on to the final section, which is a kind of a work in progress. Now, as you'll have noticed in the first slide, the Rabi oscillation is far from perfect. So if we had an ideal single qubit gate or Rabi rotation, we basically oscillate and we go all the way down, and we just get a sine squared dependence. Now, because our dot interacts with its environment, we have a lot of dephasing processes going on, and this leads to this damping. So what we've done is we've explored what is causing this damping. Now, it's worth just backtracking a little bit and to think about an ideal two-level atom system. So we've just got two levels that we're going to couple by our laser pulse. And let's imagine that we just have constant dephasing times, constant loss of coherence. Now, here I've lifted a graph from this paper here, where basically they calculate what you should observe if that is the case. What you typically observe is that the oscillation goes up and then down, and it basically oscillates between two fixed values. So the point is that the loss of coherence occurs over the first cycle of this Rabi oscillation only. Now, the reason for this is if you've got a fixed rate of coherence loss and you've got a laser pulse of a fixed time duration, then the amount of damage to the coherence of these two states is fixed. It isn't going to change as I increase the power. However, what we actually observe is something where we get a very strong damping. So as we go to higher power, we are losing coherence. So what this is suggesting is that we have a decoherence process which depends on the incident power. What this indicates is that the quantum dot is not, strictly speaking, a two-level system. It's a two-level system that interacts with an environment. Now, in semiconductors, there's no shortage of possible candidates of potential dephasing environments. And for these kind of quantum dots, the principal suspects are the wetting layer, which is basically this quantum well on which the dots sit, and the acoustic phonons, or lattice vibrations. Now, just to make things fairly brief, what we've done is we've got experimental evidence to show that the principal effect is the acoustic phonon interaction. So a model is something like this. So this is what we have mathematically. We have a Hamiltonian, which basically consists of the Hamiltonian for our two-level system. So this is basically our ground state, exciton, and we're going to couple them through the Rabi frequency. We have a term which is just due to a bath of acoustic phonons, and these are the creation and annihilation operators, and this is just the energy of a phonon with the wave vector q. But the important term is this exciton-phonon interaction, where basically if you have an exciton, then you will create and destroy phonons, and this will slightly shift the energy of the exciton transition, and these shifts in the energy will contribute to dephasing. Now, the bottom line of this theory is that when you go through all of this, you basically end up with some density matrix rate equations, which have a term which is just due to the Hamiltonian, the two-level system, and then we have a term which is due to the acoustic phonons. And the only term for the on-resonance case which is of any importance is this term which is a function of the Rabi frequency, and this causes a dephasing. So this is a reduction in the electronic polarization of this transition. And you can calculate from first principles what this should be. And if you look up it in a book, you can find out what the speed of sound of is in gallium arsenide, and you can calculate what these values are. Okay, and then we can calculate what the rate is. I'll just backtrack to give a more sort of a picture kind of what's going on. Now, the principal interaction is the deformation potential. And what this is if you create charge in the dot, that charge will basically deform the lattice, and that deformation of the lattice will change the band gap of the semiconductor, causing a small shift in the energy, and that's your deformation potential. So when we have this Rabi oscillation, what we're basically doing is we're modulating the charge of the quantum dot at this frequency omega, which is the Rabi frequency. What this means is we're going to modulate the phonons via the deformation potential at this frequency. Now, this phonon bath has a frequency response, which depends on the frequency, and this basically is a combination of the coupling strength, the density of states, and temperature kind of effects. So what you're doing is you're transferring energy from the exciton state to the phonon bath at that frequency. But because the phase space of the phonons is so large, you're going to dissipate that phase information to this vast phase space. So what you have is basically a rate of dephasing which is proportional to this function k of omega at this frequency omega. Okay, so our experimental proof of this is as follows. Here, we're looking at the neutral exciton transition, and we're just measuring the Rabi oscillations. So we're measuring the photocurrent, which is proportional to the exciton population, versus the square root of power, which is proportional to the pulse area. And we're doing this measurement for a series of pulses with different spectral widths, that is, different time durations. And if we plot these on the same scale, the first thing that you'll notice is that the frequency changes. And the frequency is changing because the Rabi frequency is proportional to the Fourier transform component of the laser pulse, which is on resonance with the neutral exciton transition. So as I increase the spectral width, all those other spectral components may contribute to the speed up of the pulse, but they do not help to drive the laser pulse. So we have this square root dependence in the frequency. Now, the other feature is that the envelope of this is independent of the spectral width. And this is telling us that the loss of coherence is a function of incident power. Now, if we think back to the two-level model, if we have constant dephasing rates, then if we have a faster control pulse, we should get less coherence loss. But in fact, the opposite is true. The more spectrally broad, the faster the pulses are, the more loss of coherence we will have. So in fact, it pays to go slower rather than faster. Now, if we do a series of measurements under the same conditions, but for many different quantum dots, And then we just rescale the pulse area to take into account that we have different coupling efficiencies. What we find is the Rabi oscillations are fairly independent of the dot. So what this is telling us is that the dephasing is an intrinsic property of the bulk material. It's not a property of the dots. Okay, here's a temperature dependent. So if you want to show that the dephasing is due to phonons, then you want to look at the temperature. So here we're going from about 15 Kelvin all the way up to 42 Kelvin. You can still see oscillations at about 60 Kelvin. And basically what you'll see is that at low temperature you have a fairly nice oscillation, but as you increase the temperature, the oscillation is more rapidly damped. One of the main points here is that when you go to the high power regime, the signal tends towards the same value, which basically is telling you that the coherence loss process is not due to the creation of carriers. This is just a pure dephasing process. Now, the red lines are fits the data. Now, the problem with trying to study this is that the rate equations do not have analytical solutions for this kind of thing. So usually if you want to fit to data and extract information, you would have an analytical solution. You'd fit your data to that. So what we're doing here is we're fitting to a numerical solution of these equations and using a genetic algorithm to find the optimum fitting parameters. And then once we do that, we can use these measurements to actually measure this kind of excitation-induced dephasing rate. So we have these rate equations, and we have a number of we reduce the number of parameters down to a minimum. So we have a dephasing rate which has a constant term and a term which is proportional to the Rabi frequency squared, and there's just a number. We also allow the amplitude to be a fitting parameter of the signal and the frequency. Then basically we put in these trial values and we calculate numerically what the solution should be. We compare that to the data to calculate a root mean square, and we use this as a fitness parameter in a genetic algorithm. And then you basically search for the optimum fitting conditions. And then when you do that, you can extract some data from this. So I've defined this excitation-induced dephasing parameter D2, which is, so this is basically saying that the rate of dephasing is equal to D2 times by the Rabi frequency. So this D2 time is a time, and what we observe is that within experimental error, it is linear with temperature. So that's the first piece of evidence that it is a phonon bath, because if you have a bosonic temperature distribution, then in the high temperature limit, and this is a high temperature limit with respect to the peak Rabi frequency. So the regime that we're looking at is we're using very slow pulses, so the Rabi frequency is relatively weak compared with the temperature. Now, we can then take this and we can fit and we can get a gradient, and the gradient we measure is, it's up here, so it's 14 femtoseconds plus minus 1.5, and that is pretty much in exact agreement with our theory. Although it's probably worth putting in a few caveats here. In theory, we make a lot of approximations, so we're assuming that it's a Markov system, etc. But the end result is very sensitive to the speed of sound, and the speed of sound is not well quoted in the literature. So there's a bit of a variation in what the speed of sound is, which can lead, depending on which value you use, can lead to big changes in this value here. So just to conclude, what we've been able to show in this final study is that one, you can observe Rabi rotations up to quite high temperatures, up to about 60 Kelvin. Two, that in a regime where the Rabi frequency is weak compared with the high temperatures that we're looking at, we can explain the damping using a longitudinal acoustic phonon model in a Markov approximation, so that's assuming there's no memory effects at all. This results in a linear dependence of the excitation-induced dephasing that you can calculate from first principles. This damping is it's a property of the bulk material. So one of the potentially interesting things about this work might be, for example, if you were to take a look at, say, a nitrogen vacancy in diamond, you can probably calculate a similar parameter and you can compare them, and this will tell you whether the excitation-induced dephasing will be better or worse in diamond. It's worth noting that in diamond the speed of sound is about more than twice that in gallium arsenide, and you've got this proportional to the speed of sound to the -5. So that does kind of suggest that diamond should be a very good material for minimizing the excitation-induced dephasing. I think the other point here is that if you look at, for example, a DiVincenzo checklist, they will talk about this ratio of the number of operation, the kind of gate time to coherence time, and that's a kind of a rough figure of merit as to how many operations you can do. But actually in a solid state system, because you're interacting with your environment, the faster you go, the more intense the driving field that you have to apply, the more coherence loss you will experience in that one operation. And so you maybe have to take this into consideration when you're designing your logic gates. That is everything. I thank you very much for bearing with me through a very long talk. And these are some references on our recent work in this field. Thanks.